Okay guys, we're now looking at question 10, 50 marker. Well, they're all 50 marks, and my email is on the screen there if you have any questions or comments about the marking scheme. Now question 10 has 3 parts, A, B and C. You must do 2 of them, okay? Or you can do all 3, but it's the best 2 marks that are counted, okay? So A, B or C. So our first one is a stoichiometry one, calculations. So aluminium is made from bauxite ore, which is an impure oxide of aluminium. Aluminium oxide is reduced to carbon to form aluminium and carbon dioxide, and we have our equation there. So the first question is how many grams of aluminium oxide are needed to produce 540 grams of aluminium metal? So the relative atomic mass of aluminium is 27. So 540 divided by 27 gives us 20 moles of aluminium. So 3 marks for getting that far. We then look at our ratio of aluminium oxide to aluminium. It's 2:4. So that means we divide our 20 by 2 to get us 10 moles of aluminium oxide. So then the relative molecular mass of aluminium oxide is 102, and here your addition must be shown for an error to be treated as a slip, which would just mean a loss of 1 mark. So the mass of aluminium used is 10 by 102, which is 1020 grams. On to part 2, it is assumed that bauxite is 50% aluminium oxide. How many grams of aluminium can be produced from 1 kilogram of ore? So we have 1 kilogram, which is 1,000 grams of ore. We divide that by 2 to get our mass of aluminium oxide, which is 500 grams. So then you get the moles of aluminium oxide, 500 divided by 102, which gives us 4.9 moles. Now, if you had made a mistake in adding up the relative molecular mass of aluminium oxide in the previous part, you can continue to use that incorrect value and not lose any marks. Okay, so then we have the ratio of aluminium oxide to aluminium, which is 2:4. So if you have 4.9 moles of aluminium oxide, then you have 9.8 moles of aluminium. Okay, so then the mass of aluminium used is those 9.8 moles multiplied by 27, which is 264.6 grams, so 3 marks. That's what we see where we get our lots of 3 marks for that part of the question. On to part 3. If 826 kilograms of aluminium oxide reacts with 252 kilograms of carbon, identify the limiting reactant in this reaction, and then calculate the volume of carbon dioxide produced when it's measured at room temperature and pressure in this reaction if there is a 57% yield. So first of all, you work out the moles of aluminium and the oxide and the moles of carbon formed. So we have 826 kilograms, which is 826,000 grams, divided by 102, gives you 8,098 moles. Then we have 252 kilograms of carbon, which is 252,000 grams, divided by 12, which gives you 21,000 moles. Okay, so you work out the limiting reactant there. So we see from our equation on the previous page that the ratio of aluminium oxide to carbon is 2:3. So we're going to take the 8098 moles of aluminium oxide and we'll apply the ratio to it. So you multiply by 3/2 or divide by 2 and multiply by 3, and you get your 12,147 moles of carbon is needed to fully react with the aluminium oxide. Now we've already worked out that we have 21,000 moles of carbon, okay, which is the equivalent of the 252 kilograms. Now we have 21,000, we only need 12,147, so we've way more carbon than we need. 21,000 is obviously greater than 12,147. So carbon is in excess and aluminium oxide is the limiting reactant. So there's your, so to get the first 3 marks, you must have both the 8,098 and the 21,000, and then you go on and get your limiting reactant being aluminium oxide. We continue on then, and our ratio of aluminium oxide to carbon dioxide is 2:3. You use the aluminium oxide as your starting point for the ratio, so that gives us 12,147 moles of carbon dioxide. We multiply that by 24 because it's room temperature and pressure. The molar volume at room temperature and pressure is 24. That gives us 291,528 liters. It's 57% yield, so 291,528 by 57% is 166,170.96 liters, and thereabouts in and around that value will give you the marks there. So 3 for getting the theoretical yield and 4 for getting your final answer, for a total of 13 marks there. Okay, on to part B. This is a radioactivity question. So thallium-201 is a radioisotope used to determine cardiac tissue damage and cardiac stress tests. The half-life of thallium-201 is 73 hours. Explain the underlying terms. So radioisotope, okay, that is an unstable nucleus, an atom with an unstable nucleus. A nucleus decays are a radioactive isotope. So any one of those will give you the 3 marks. Half-life is the time for half the sample to decay. or for the activity to reduce by a half. Again, either of those two options will give you the 3 marks. Thallium-201 decays and emits gamma radiation. Alpha radiation is another type, named the third type of radiation and state one of its properties. So beta radiation gives you the 3 marks. Properties: the neutron changes to a proton, and an electron is emitted. It's negatively charged, it's negligible mass, it's less penetrating than gamma, it's more than alpha. It damages cells and causes cancer mutations. It's deflected by magnetic fields or causes electroluminescence. So any one of those 3 will give you the marks there. Okay. If 10 milligrams of thallium-201 was used in medical assessment on the patient, how many hours will it be until 2.5 milligrams of this isotope still remains? So it's 146 hours, and that's hit or miss. So how do we work that out? Well, 10 divided by 2 is 5 milligrams. So that's 10 milligrams which you start with. That took 73 hours because that was the half-life of thallium-201. And then 5 divided by 2 is 2.5 milligrams. And that took another 73 hours. That's a total of 146 hours. Nuclear reactions give rise to transmutation. What is transmutation? And give 2 differences between nuclear reactions and chemical reactions. Transmutation is where a new element is formed, 3 marks. And a chemical reaction, a nuclear reaction, the differences, you can see them there, there's loads. Chemical involves electrons, nuclear, the electron cloud is not involved. Chemical, there's no change to the nucleus. There is a nuclear change in the nucleus. Chemical is bonds broken, there's no bond breaking. The elements are unchanged. In chemical, elements or new elements are formed. In nuclear, and the mass is conserved in chemical, and the mass is not conserved in nuclear. Okay. So there you go. There's how you get your 7 marks there. And on to part C. So a lab wants to carry out some drug tests on athletes. It has a mass spectrometer and an ultraviolet spectrometer. Drugs have been found in the athlete's systems, and the lab wants to determine what mixture of chemicals make up the drug and what quantity of each part of the mixture is present. State the principle on which ultraviolet spectrometry is based. Absorbance is proportional to concentration, and that's it. Full marks there for getting that. Outline the fundamental processes that occur in mass spectrometry. So we have vaporization, ionization, acceleration, separation, and detection. So those 5 words there, you get 3 each for the first 4 and 1 mark for detection then, a total of 13. And then naturally occurring silicon consists of 92.23% 28 silicon, 4.67% of 29 silicon, and 3.10% of 30 silicon 30. Should be saying it the other way around, but anyway. Calculate the relative atomic mass of silicon. So you multiply the percentage by the mass number, so 92.23 by 28 plus 4.67 by 29 plus 3.1 by 30, all over 100. And that gives you 28.18087, and you can see where the marks are given there. Okay, so that's question 10 done and dusted.